Asymptotic notation in equations and inequalities. We have already seen how asymptotic notation can be used within mathematical formulas. For example, in introducing big O notation, we wrote n equal to big O of n square. We might also write 2n square plus 3n plus 1 equal to 2n square plus theta of n. So this part got replaced by theta of n. How do we interpret such formulas when the asymptotic notation stands alone, that is not within a larger formula on the right hand side of an equation or inequality, as in n equal to big O of n square? We have already defined the equal sign to mean set membership n belongs to big O of n square. In general, however, when asymptotic notation appears in a formula, we interpret as standing for some anonymous function that we do not care to name. For example, the formula 2n square plus 3n plus 1 equal to 2n square plus theta of n means that 2n square plus 3n plus 1 equal to 2n square plus function of n, where f of n is some function in the set theta of n. In this case, we let f of n equal to 3n plus 1, which indeed is in theta of n. Using asymptotic notation in this manner can help eliminate inessential detail and clutter in an equation. For example, in chapter 2, we express the worst case running time of a merge sort as the recurrence t of n as 2 into t of n by 2 plus theta of n. If we are interested only in the asymptotic behavior of t of n, there is no point in specifying all the lower order terms exactly. They are all understood to be included in the anonymous function denoted by the term theta of n. The number of anonymous functions in an expression is understood to be equal to the number of times the asymptotic notation appears. For example, in the equation summation of I equal to 1 to n big O of I, there is only a single anonymous function, a function of I. This expression is thus not the same as big O of 1 plus big O of 2 plus big O of 3 till big O of n, which doesn't really have a clean interpretation. So this big O of I is one expression, and it is a constant. Is it what they are trying to tell? It is equal to the number of times the asymptotic notation appears. Okay. There is only a single, okay, in some cases the asymptotic notation appears on the left hand side of the equation as in 2n square plus theta of n equal to theta of n square. We interpret such equations using the following rule. No matter how the anonymous functions are chosen on the left of the equal sign, there is a way to choose the anonymous functions on the right of the equal sign to make the equation valid. Thus our example means that for any function f of n belonging to theta of n, there is some function g of n such that belonging to theta of n square such that 2n square plus f of n equal to g of n for all n. In other words, the right hand side of the equation provides a coarser level of detail than the left hand side. We can chain together a number of such relationships as in 2n square plus theta of n equal to n square. We can interpret each equation separately by the rules above. The first equation says that there is some function f of n belonging to theta of n such that 2n square plus 3n plus 1 equal to 2n square plus f of n for all n. The second equation says that for any function g of n belonging to theta of n such as the f of n just mentioned, there is some equation h of n belonging to theta of n square such that 2n square plus g of n equal to h of n for all n. Note this interpretation implies that 2n square plus 3n plus 1 equal to theta of n square, which is what the chaining of equation intuitively gives us. O notation: this is a small o when compared to the big O. The asymptotic upper bound provided by the big O notation may or may not be asymptotically tight. The bound 2n square equal to omega big O of n square is asymptotically tight, but the bound 2n equal to big O of n square is not. We use small o notation to denote an upper bound that is not asymptotically tight. We formally define small o of g of n as little o of g of n as this set f of n for any positive constant such that there exists 0 less than or equal to f of n less than or equal to c. Okay, isn't this the same as big O of n? For example, 2n equal to of n square, but 2n square is not equal to of n square. This is not an asymptotically tight, okay? I think I'm getting it. What they're trying to say is they're directly saying that that is not tight by using a small o notation, little o notation. The definitions of big O notation and O notations are similar. The main difference is that in f of n equal to big O of g of n, the bound holds for some constant, but in oh, okay. Let us go for this big O notation. This is the definition for a positive constant c. But there's for c for all c greater than 0. Some some authors use this limit as a definition of the small o notation. The definition in this book also restricts the anonymous functions to be asymptotically non-negative. This is a little omega of g of n by analogy. Little omega notation is to the omega notation as small little o notation to the big O notation we use to denote the lower bound that is not asymptotically tight. One way to define is that belongs to small little omega only if g of n belongs to. So basically what they are trying to tell us, if this is the if the if for g of n the upper bound is f of n, then for f of n the lower bound is g of n. Formally, however, we define such that for all c greater than 0, for example, n square by 2 equal to little omega of n, but n square by 2 not equal to little omega of n square, the relation f of n equal to little omega of g of n implies that, okay, if the limit exists, that is okay, this limit, if the limit exists, is important. That is, f of n becomes arbitrarily large relative to g of n as it n approaches infinity. Comparing functions, many of the relational. How long is this chapter? Let's complete it. Comparing functions, many of the relational properties of real numbers apply to asymptotic comparisons as well. For the following, assume that f of n and g of n are asymptotically positive. Transitivity. F of n equal to theta of g of n and g of n equal to theta of h of n imply f of n equal to okay. And big O of h of n, okay. This they're just trying to tell that if one is greater than less than 2 and 2 is less than 3, then 1 is less than 3. Reflexivity, if f of n equal to theta of f of n, what does it mean? What does it mean? Symmetry, then if and only if g of n equal to theta of what? Let's say n square equal to theta of g of n, then I'm not getting it. Transpose symmetry. We can run analogy between asymptotic comparison of two functions for f and g and the comparison of two real numbers a and b. For any two real numbers a and b, exactly one of the following must hold. Although any two real numbers can be compared, not all functions are asymptotically comparable. That is, for two functions f of n and g of n, it may be the case that neither f of n equal to big O of g of n or f of n equal to omega of g of n holds. For example, we cannot compare the functions n and n to the power 1 plus sin n using asymptotic notation, since the value of the exponent in n into n to the power 1 plus sin n oscillates between 0 and 2, taking on all values in between. We have exercises. I'm going to skip it for now. Standard notations and common functions. This section reviews some standard mathematical functions and notations and explores the relationships among them. It also illustrates the use of asymptotic notations. Monotonicity. A function f of n is monotonically increasing if m less than or equal to n implies f of m less than or equal to f of n. Similarly, it is monotonically decreasing. Okay, a function is strictly increasing. Okay, we know all this, floors and ceilings for any real numbers. Okay, basically what they're trying to tell us, if a is less than b, let's say the function f of n is n plus 3. If when n equal to 1, f of n equal to 4, 3 plus 1. But when n is equal to 3, f of n equal to 3 plus 3 equal to 6. So 1 is less than 3, and the output f of n 4 is less than 6. That is what they are trying to tell. Increasing, decreasing for all m less than or equal to n, that condition should hold true. Floors and ceilings. For any real number x, we denote the greatest integer less than or equal to x by this notation, and the least integer greater than or equal to x by. For all real x, x minus 1 is less than or equal to x, and this x minus 1, for example, if let's say x is 6.5, the floor of x 6.5 is 6, which is still greater than 5.5, and it is the seal of 6.5 is 7, which is still greater less than 7.5. And for any integer n, the n by 2, let's see, let's take an odd number, uh, or let's take 6.5 again. N by 2 is 3.25. 3.25, you are sealing it. 3.25 to the floor is 4, and 4 plus 3.25 seal. You are sealing it, so or flooring it, it becomes 3. 3 plus 4 is not equal to n. How are they doing it? It is not equal to n. Okay, they have given for an integer. We need to ignore the decimal part. Let's take the value is 7. 7 by 2 is 3.54. It becomes 4 and 3, it gives 7. And for any real number x greater than 0 and integers a comma b greater than 0, these hold true. For now, we'll take these values because, of course, they would have proven it, and we can prove it. It's simple mathematics. We just have to take any example and prove it. Or if we need to disprove it, we need to prove that for this example it doesn't happen. But then it is still simple mathematics. Modular arithmetic. For any integer a and any positive integer, and the value a mod n is the remainder or residue of the quotient a by n. This is in programming. We generally use the percentage sign. 7 mod 2 is 1, because the remainder is 1. Given a well-defined notion of the remainder of one integer when divided by another, it is convenient to provide special notation to indicate equality of remainders of A mod n equal to B mod n. We write K is equivalent to B. Modulo n, in other words, if A and B have same remainder when divided by an equivalently if and only if n is a divisor of b minus a. Okay, what they are trying to tell us, let's say the number 35 and 38, all right? And let's take the n equal to 3. 35 modulo 3 is the remainder is 2, and 38 modulo 3 remainder is again 2. 35 and 38 are equivalent to each other modulo 3. And what they are trying to tell us, if the remainder between after dividing is the same, the difference should be divided without remainder by the n. So 35 minus 38 is 3, which is divisible by 3. Polynomials. Okay. Polynomials. Okay. This we write a is not equivalent to b with a scratch symbol on there. Now, polynomials given a non-negative integer d, a polynomial of an n of degree d is a function, okay, where I equal to 0 to d n to the power d and summation till n to the power 0, where the constants are coefficients of the polynomial and a of d is not equal to 0. Okay, a polynomial, the highest degree coefficient shouldn't be 0. The remaining can be 0. For example, x to the power 5 plus x power 4 plus x power 3 plus x power 2 plus x power 1 is a uh, polynomial in n of degree 5, and x power 5 plus 1 equal to 0 is still a polynomial in n of degree 5. Polynomial is asymptotically positive if and only if a of d is greater than 0. For asymptotically positive polynomial of degree d, we have p of n equal to theta of n of d for any real constant. We have seen this earlier. For any real constant a or a greater than or equal to 0, the function n of a is monotonically increasing. And for any real constant a less than or equal to 0, the function n of a is monotonically decreasing. We say that a function is polynomially bounded if f of n equal to big O of n to the power k for some constant k. Okay. For all real a for all real a greater than 0, what they are trying to tell here is monotonically increasing. Let us take a real constant a equal to 5. 2 to the power 5 is less than 3 to the power 5 is less than 4 to the power 5. It is monotonically increasing. Exponentials for all real a greater than 0. And then we have the following identities: a of 0 equal to 1, a to the power 0, 1, a to the power 1 is 1, minus 1, mn, okay, and interchangeable. And when the base is same, you can add the powers. For all n and a greater than 1, the function a of n is monotonically increasing in n. When convenient, we shall assume 0 to the power 0 is 1. We can relate the rates of growth of polynomials and exponentials by following fact: for all real constants a and b is such that a greater than 1 and n tends to infinity. Okay, this is 0 and n tends to infinity, infinity to the power b. We don't know the value of b, but then we do know some value of which turns to infinity, from which we can conclude that n to the power b is asymptotically bound by little o of a of n. Thus, any exponential function with a base strictly greater than 1 grows faster than any polynomial function. That is what they are trying to tell. What they are trying to tell is a to the power 5 grows than a polynomial in the degree of 5, like x to the power, how do you say it? X to the power 5 plus 1, for example. Using E to denote 2.7.2.71828, the base of the natural logarithm function we have for all real x. There is a proof for this. We are not going to see this now, but the summation comes to this: x of I by I factorial I equal to 0 to infinity. For all x, we have the inequality where, okay, these are all mathematics logarithms. Log of n equal to log 2 binary logarithm to the power x equal to n. This is what it means. A natural logarithm is to the base e. When you write log, log it is to the base 10 usually, and an important notational convention we shall adapt is that logarithm functions will apply only to the next term in the formula. So will mean, okay, not to if we hold p is greater than one constant, strictly increasing, okay? If b is constant and for n greater than 0. What it means is, for example, uh, log of 5 to the base 3 or log of 9 to the base 3 is equal to 2, but log of 27 to the base 3 is 3. Is it? Yeah. So when n is increasing, the output is increasing for all real. We have the properties of logarithms. This property is that b to the power log of a to the base b, these can be substituted. Multiplication turns out to be addition of the individual logarithms, and this power comes out, and this is the splitting of changing the basis. When the base is common, we can put the denominator as the base. There are proofs for all of this again, but this is just this property to the power. This becomes a to the power minus 1. This power goes outside, same as this property. Log of b, log of a to the base b. This can be written as log of a to the base a by log of. Okay, there is proof. We are not going to say it for now. And okay, where in each equation logarithm bases are not one by equation 3.15. Changing the base of an algorithm from one constant to another changes the value of logarithm only a constant factor, and so we shall use the notation log. And when we don't care about constant factors such as in O notation, computer scientists find 2 to be the most natural base for logarithms because we so many algorithms and data structures involve splitting a problem into two parts. There is a simple series expansion for natural logarithm of 1 plus x. We also have the inequalities. We say that a function is poly logarithmically bounded if, okay, this is again the mathematics. The notation n factorial read as n factorial is defined as, okay, this is a recursive call. Weak upper bound on factorial function is n factorial is less than n power n, since each of the n terms in the factorial product is at most in Stirling's approximation. N factorial is equal to root of 2 pi n by e to the power n and 1 plus theta of 1 by n, whereas the base of the natural logarithm gives us a tighter upper bound and a lower bound as well. As exercise asks you to prove, okay, the Stirling's approximation is helpful for the following equation, okay. Functional iteration, we use the notation f of I, f to the power I of n to denote the function, and iteratively applied I times to an initial value of n formally Let f of n be a function over the reals for non-negative integers I. We recursively define f of n to the superscript I equal to be equal to f of f. Okay, we are decrementing I, and when I equal to 0, it is n. So for the final part, this becomes f of n. For example, if f of n equal to 2n, the iterated logarithm function. We are almost done. Let us complete it. We use the notation log star n, it as log star of n. The iterated logarithm function defined as follows. To denote the iterated logarithm defined as follows, let log of I superscript I to log of n superscript I be defined as be defined as be as defined above, with f of n equal to log of n. We need to remember that LG is binary logarithm to the base 2, because the logarithm of a non-positive number is defined only if logarithm of a negative number is undefined. Non-positive in the sense even for 0. Be sure to distinguish the logarithm function applied I times in succession starting with an argument n from logarithm of n raised to the ith power. Then we define the iterated logarithm function as follows. Log 2 22. Okay, I'm not understanding it. Okay, basically what they're trying to tell us, when you repeatedly apply this log function, keeping an n, for example, let's say log of 2 to the base 2, this value is 1 straight away, but then for log of 2 to the base 1 at log of 1, it becomes 0, then it is not defined again. For 4, what it goes. Okay, this chapter is done. We then go through the exercises. We can start with the next chapter.